then in this remaining 45 minutes, we're going to talk about the boson sampling, which is another sub-universal model, very important historically, proposed by Aronson and Archipov in 2013. And so this model, technically speaking, should not stay here, but it should stay in the lectures of within two weeks from now, because it is not about qubits, but it is about bosons. And then it's a different mathematics, it's a different space. I will give a little bit more introduction to bosons and quantized harmonic oscillator in 10 days from now. For today we don't need much. I just wanted to make you notice that it's not qubits anymore. So is there somebody who never heard about the quantized harmonic oscillator and a dagger, or is fine? So then, this circuit works like this. We have a certain number of modes. So then these are not qubits, but modes of the electromagnetic radiation. It could be, for instance, modes of optical light. And then in a certain number of modes, we have single photons. Notice that now this 1 is not the qubit state 1, but is a dagger applied to 0. So the creation operation of the field applied to 0, it means 1 excitation, while 0, it's a state that is has no excitation. And in the other modes, so let's go through this. In the other modes, we have vacuum. The number of modes in which you have single photons is what defines the size of the problem, and it's called n. While the total number of modes is called m. And then we have a unitary transformation that physically corresponds to linear optics. It's a passive transformation that doesn't create energy, so there is no squeezing whatsoever. In practice, you can think that these are photons that go inside the optical fibers, and then you can think that you are coupling in an evanescent way the fibers. You are putting them close to each other, and the photons have a non-zero probability to hop from one fiber to the other. How they do this? It's very nice. There is a group in Rome, the group of Fabio Sciarrino, where they take silicon blocks like glass, and they have like some fancy way of with thermally in changing the refractive index even in the bulk, so they can even construct 3D interferometers of this kind. And then at the end, we measure the presence of photons. So typically, you might want to have a single photon detector, but if the number of input photons is much smaller than the total number of modes, then the probability of obtaining 2 output photons in the same mode is negligible. Then it's enough to have an on-off detector that only discriminates between 0 and 1, because you don't need to resolve a 2, because the probability of having 2 is suppressed. It's what they call the birthday paradox. So then typically n is much smaller than m. Birthday paradox if n is of order of square root of m already. So this is already good to suppress the probability of having 2 photons. So then what we have is that we are going to just sample, run this experiment many times, and then record where are the photons. Then we are going to get a sample of the kind like 0, 1, 1, 0, 0, 1, and so on and so forth. Every time something different. And the statement, so what is possible to prove is that the probability distribution, so let's call the input initial state like A dagger 1, A dagger n, on 0, 1, 0, m, small m, I call them small m. So these are your m modes, and only in the first n you have a photon. And then the output state is some kind of state that correspond to a certain configuration like this. So this time I have to put for each mode, this is dagger, yes, m. So S is what tells me if I get 0 or 1. So then I have to take all of the operators, but to the power S. So this typically can be 0 or 1. Note that in general it will be 1, 2, 3, 4, 5 if you start with many photons. So then for a general configuration S of outcome, the probability distribution P of S, which is S U T modulo square. So one can show that this is proportional to the permanent of a submatrix S that we are going to write over, in general, S1 factorial, Sm factorial. In the case where you only have 0 or 1 photons in the outcome, of course this is equal to 1. So in this expression there is this permanent appearing, and I also have to tell you what is the submatrix S. Let's see what is the permanent before. So the permanent of a matrix A, let's say for example of A, B, C, D, F, G, H, I, L. So it's like the determinant, but where you take plus everywhere. So then in this expression it will be A that multiplies PL plus AGI plus B DE plus BGH, and so on and so forth. And you see that in contrast with the determinant, so with the determinant you have some minus sign, which eventually allows you to find an algebraic expression that simplifies the calculation out. So you can compute it. While for the permanent, you have to evaluate all the possible combinations of products in the matrix. So that's one of the reasons why it takes a combinatorial number of terms. It involves a combinatorial number of terms. So in the notes, I really put yeah, there is another thing that I have to tell you. What is this submatrix US? So US is the submatrix where you take the rows of U. U is the matrix that describes the interferometer, that correspond to where you have the single photons. So in this definition of the model is the first n rows. And then you have to repeat the columns as many times as Si. So then repeat column J Sj times. Let's make an example to clarify the ideas. So let's say that we observe the state 0 to 0. Okay, we are not going to observe it if, but let's make an example to explain what the matrix is. So then if we have a matrix U that is U11, U12, U13, U21, U22, U23, U31, U32, U33, then US in this case would be, so the first rows are these two, and then I should take the column 2 repeated twice. So this will be U1, 2, U1, U2, 2, U1, 2, U2, 2. This is the thing. And then the probability of the state 0 to 0 is given by the permanent, and I have to take it modulo square, and I have to divide by 2 factorial. And I have to take then twice, because it's twice the same term, U12, U22, and then this is modulo square. So then this is equal to 2U12, U22. That's to fix the ideas.
Can you say how you got US once more?
Yes, you have to take the rows where you have the single photos. So in this simple case, I fix the model like this. So then it's always going to be the first n rows. Here n is equal to 2 because I have 2 photos. So I have to take the first 2 rows, which are these 2. And then you have to take the columns where you have a photos in the output. In this case, it's column 2.
Okay.
And you have to repeat it by the occupation. That is 2 here. So in this case, I have to repeat twice this column. That's why I copy U12,
Okay.
U22, U12, U22. I copy it twice. And then you get the probability as this permanent. And okay, so then in the notes, I actually put the full calculation. That shows, so this is an example, I put really the demonstration that you get this, if you calculate this, so the demonstration to go from here to here. And it's a terrible combinatorial thing. I'm sure that if I try to do it, I will get it wrong. So, but I would invite you to take a look if you want. It's a second quantization calculation with configurations and combinatorial to take into account. And the number of, by the way, about the combinatorial, the number of total configuration, it's n plus m minus 1 divided by n. So it's a very large number, and it's why we are going to explore the full, here it doesn't make much sense. Yes, it's the full Hilbert space of n photons in this sense. All the possible output configurations are going to contribute to the probability. And then maybe one other thing to mention is that, so in the original paper by Scott Harrelson, he gives 2 different proof of hardness for this model. One is exactly the same sketch that I mentioned for IQP, and indeed it is inspired by IQP. He says really, but that's the second one, so it's not his first proof. He gave his first proof, and then he said, I saw this nice paper by Bremner about IQP, and that kind of proof works even here. So here, how does it work? What you want to show is that if you add the post-selection, this boson sampling becomes universal. And we are not going to do all the details, but I wanted to convince you that it works. And it works because the underlying computational model that he uses to prove this is the so-called, so let's say, proof of hardness, only sketch this time. And there are 1 and 2. So this one is the 2, and is like IQP. So it's based, so which means adding post-selection, boson sampling becomes universal. And it uses a model that is called KLM by Nilla, Flam, and Milborg. That is a universal model of quantum computation that we didn't see in the course. And it's based on quantum optics, where you use a dual Rayleigh encoding. And basically you encode qubits in optical modes such that the 0 logical is 1, 0. So you use 2 optical modes to encode 1 qubit. And then the 1 logical is the 0, 1. So it's 1 photon in 2 modes of the radiation. And depending where is the photon, you get either the 0 qubit or the 1 qubit. So then what happens? Of course, you can interpret then the boson sampling a little bit like this, where then you have some qubits in the input, depending on how you define the dual array qubits, and you want to leave freedom to that. And then the idea is that in this model, single qubits operations, universal single qubit operations are achieved by linear optics. With the U, you get single qubit operation. In dual array encoding. And then the idea is that with post-selection, so what is missing is a 2-qubit gate. And then with post-selection, you get a 2-qubit gate. And then you show that post-selected boson sampling is universal because of this underlying KLM. And then the rest of the proof goes like before. So the rest of the, you could say, suppose that boson sampling is efficiently classically simulatable, then post boson sampling is containing post BPP. Then because if you add the post selection, it becomes universal, then you will have post BPP equal to post BQP, and this leads to the collapse of the polynomial hierarchy. So the rest of the proof is exactly the same. And then the first one, we are really not going into see the detail, but it's also based on the collapse. It's based on showing that approximating boson sampling probability distribution is sharply hard. And eventually you would get that if boson sampling would be efficiently simulatable classically, then here the thing would be that P to the sharp P would be equal to BPP to the NP, and this is also implying a collapse to the third level. But we are not going to say much more than this. And what is remarkable is that there is, even in this case, it's possible to give both an approximate case, an approximate result, that the sampling even from a distribution that is approximately the one of boson sampling is computationally hard classically, and even here it's possible to give an average case statement. So if you take with the hard measure random U, then the probability that you get a hard to sample circuit is very high. You can bound the probability that you lead to a trivial circuit. So we have approximate case, and then we have the average. The only thing is that here the approximate result is based on extra conjectures, while in the case of IQP, these conjectures have been proven. And here they have not been proven. But Scott Aronson has numerical evidence and intuition. And so I didn't even write what they are, but they are called the Gaussian permanent conjecture, and there is a second one. I'm not sure I wrote what they are, but it becomes really a technical discussion then. Do you have questions about boson sampling?
Yes.
Mm.
So isn't this very similar to IQP then? Like, couldn't you do boson sampling with qubits? If if the number of excitations are few, like here, and it's much smaller than n, you could prepare qubits. Some qubits, if you have 20 qubits, prepare 2 of them in 1, rest in 0, and then implement unitaries that just preserve the number of excitations in the system, and you measure the computational basis.
In IQP?
No, like in the I mean, it would be like boson sampling, but with qubits, right?
Yeah, you
Then
do qubits, but with just swap operations.
Yeah. Let's say the unitaries are different kind of I-swaps or swaps. You sort of preserve the number of excitations in there, and then you measure in the computational basis in the end, then you get zeros and ones, and you should get the same ones of 1 in the end than you had in the beginning.
I'm thinking, I think this is not possible. The mathematical structure is very different. Let me think. What are these U doing? This U, so what you say is that you would like to mimic the unitaries here
Yes.
with qubit operations.
Which we should be able to do, right? Because we can do any unitary, because we have a universal gate set. So I can do any unitary I want.
But mathematically it's very different objects. So I'm I never thought about this question.
But so then, because as long as the number of excitations in one mode does not exceed 2, then if it's just 0 or 1, then it should map on a qubit directly.
Yeah, I see what you mean. But then about the operations, I'm not sure. Because the only thing that, so now you are proposing something that is, so here you see, here they do like this. So what you're proposing, it's a different encoding. So let's call it Andreas. You're proposing 0 logical is 0,
Yeah.
and 1 logical is 1.
Yeah.
So let's think. A single photon, so let's say if you want to have, I don't know, X logical, then will be a dagger, I guess. Is it true? No, it only works if I apply it here.
Yeah, but as long as you're in a state, like
Yeah.
as long as there is nothing in the second state of the bosonic mode, the mapping should be.
So you see, this already doesn't work, by the way, because if I apply a dagger to 1, I don't get a 0. So it works only from here to here, but it doesn't work from here to
Okay,
here.
so then can we do an encoding where we take 2 qubits and then we just define the same dual rail and then just have swap operations?
With dual rail you can.
Yeah.
You can map dual rail to
A qubit.
qubit. That would you could do.
Sure.
So that would be probably the way that I would see
But
it.
in this linear in the unitary here, there are no A dagger terms, right? Like
No, but
Did-
what does it mean? Wait.
because
yeah.
you preserve the number of excitations
Yes,
in
you do preserve the number.
So
of
you don't need to
excitations.
So you don't need to have the access to a dagger, because that is not in there.
Okay, but then what are the qubits operation that would mimic such a thing?
Like I-swap, for example, so that's a beam splitter. It's the same Hamiltonian splitter, and you can do phase shift. This is what you do in linear optics, right? You have phase shifters and beam splitters. I don't think you have anything else. And this you can mimic.
But I'm very puzzled because typically what is crucial here is the fact that the bosons interfere with each other and then they give rise to some pattern of distribution. So I would be very puzzled if you could do this. I mean, even with qubits, we know that we are going to populate in the IQP or the full inverse space, but I'm not sure 100% that you could reproduce this is like bosonic statistics with qubits. I have to think a little bit about it. For me, it's not trivial. I see what you mean, but then I would like to be convinced that all the unitaries and not only some trivial ones could be mapped to qubit. Unless it is with dual rail, and then yes, it is
I don't think it's
possible.
single.
But I will think about it. It's interesting. It's a very good question. Yeah. Okay, and we have roughly, say, 10 minutes. Maybe it would be worth spending, just to mention, because it has been done, this Google experiment. I will probably not add much to what you know already because I will not go into the details. But since it has been such a milestone, I think it's worth spending a minute. That can be then more of discussion when we put together what we know than of actual course. So I can start by telling you what I know and what I understood for the moment. In the notes, I've only put the official WACQT statement after the release that was prepared by Joran. And I have edited because he prepared it before the IBM experiment or simulation.
No, not even that. They didn't do it.
They didn't run it.
And they said that they can run it.
They said they can run it, they didn't say they did run it.
But they said it would cost $800,000 to run it.
Yeah.
'Cause
Every,
that's the estimate they gave.
every what?
$800,000
For,
to run the calculation across all the supercomputers.
$100,000.
So-
$800,000.
Okay, they should do it because they went too far.
I don't think they can actually run it because the problem with putting all that into memory without having any redundancy in the memory is if you get a cosmic ray flipping a bit, it just ruins the entire calculation.
If you get what?
If you get, say, a cosmic ray hitting a bit in the memory, if you're using the entire
Oh,
memory
yeah,
structure
yeah,
without
yeah,
any
yeah.
redundancy,
Yeah.
destroys the calculation immediately.
Okay. Yeah.
So I don't think it can
Yeah.
physically be run.
yeah. I saw a talk by John Martinez when he commented on the result, and he sort of invited them to please do it.
Yeah, please do it.
And-
Sure, they said they
and-
should do
and-
it
and-
after.
His, sort of, he, reading between the lines, he said that it's not able to be done. Because they're using the full disk space of this thing, just to sort of store the state of 53 qubits.
Mm.
If you get one bit flip anywhere, you're screwed.
Yeah.
And if you're just using the full memory, you can't do any sort of classical majority vote error correction on this large state.
Mm.
Since you have 300 petabytes or whatever it was,
Yeah.
the probability of having bit flip is actually quite high.
Yes. But still, between 2.5 days and 1,000 years, there is a long.
Yes.
Yes.
So probably the truth is somewhere in between. Maybe if they would.
So it's like, adding one more
Yes,
qubit
yes.
doubles, then you need two
Yeah, yeah.
subvoltages.
With one more qubit, it's impossible. I mean, it's that's why I'm very
Yeah.
impressed anyway by the. I am one of those who are very impressed.
Which is very unfortunate that the one qubit wasn't working on the Google device and they had 53 instead of 54.
That's true, because otherwise IBM could not even have.
Yeah, they couldn't even make this.
But still, this gives an idea of how much at the edge we are with this simulation capability. So then this is about random circuit sampling. And what we know is that this time the circuit structure, so the states are prepared in 0, and then there are like random gates here that can be summed to cubic gate and so on and so forth. And these gates can be of three kinds: either square root of x, or square root of y, or square root of w, where w is x plus y. So this is what gives the no-Clifford power. So this is why the circuit is outside the Gottesman and Neal hypothesis. What makes it computationally hard? If you would not have this would be Clifford operations, and you would then be able to simulate this efficiently because the states are prepared in 0, and then you also measure in the computational basis. So what I wanted to say is that there is a computation, so a proof of computational hardness that is given in a reference. In Poland et al. And then what I know, so a big question that people have been asking is how were they sure that they are sampling from the right distribution that correspond to these circuits? Sure, they have a very good and calibrated gates with good gate fidelity, but how do they know that they are not too far, that they are not sampling from a probability distribution that is not the one that is predicted here to be hard to sample? And then for this they do two things. One is that they can simulate efficiently classical this when they remove the W, so for the Clifford gates. So tests to check the output. They have two. One, remove the square root of W, so only Clifford. And then it is simulatable and they check it. And the second one, check the full structure of circuit, but for smaller circuits. And they also get a good agreement. And then they are convinced that it should be good. I mean, it's an indication. I would like to dwell a bit more in that, to study myself a little bit more the papers on verification of this model. I'm not, I still didn't do much work on that. Yes, and otherwise, as we have been mentioning, it's even if today, so there has been this release by IBM saying that with their supercomputer, which is the most powerful on Earth, they could simulate this model with the 52 qubits. And it will be very, very, very desirable if they would do it, because they would then verify the output probability distribution for this size of circuit, and then of course if now Google puts more qubit, it will not be possible anymore. But since they made a statement that it is possible, I really believe that they should do it. Because it's really, for Google also, it's good for everybody. It would be a stronger result. It would be very, very good. Yes, I don't think, somebody wants to add something about this model. Probably everybody read the paper.
Reproducibility is good, and if they can have a way of reproducing it, that only adds to the science.
One other thing that I could mention is that, for instance, for those who saw the talk by Isaac, there was already, it has already happened in the community that physicists produce an experiment that cannot be simulated efficiently classically. For instance, there was this experiment by Emanuel Bloch with the cold atoms trapped in optical lattices, where they were preparing a state, then giving a kick and observing the thermalization. And then there were some relevant observable in time that was then doing something like this. And then the classical simulation was able to simulate up to a certain time, but then it was too costly to go further, while the experiment was obviously continuing. So this was taken as a first demonstration of a quantum simulator doing something beyond the regime of simulatability. The two striking differences of the Google experiment with the Block one are first that this is computationally proven to be hard to sample, while this is practically hard. Maybe it is also provably hard, but nobody proved it. So it's more that practically we know that it's complicated to simulate such many body interacting systems. So first, this is provable, and second, this is reconfigurable. So the next step from here is to switch the gates to actually build a computation, so to actually do a useful computations. So this is towards a computer in the sense of a programmable device. And this is, it's a special purpose quantum simulator. It's a little, much less versatile in this sense, much further from what our intuition of a computer should be.
I mean, this is a philosophical question, right? What is a what is an analog quantum simulator? Because I could just take some two chemicals and mix them, and you can't calculate the chemical reactions going on, but I obviously performed them right.
Now, you would, for a simulator, you would be able to map, you have a system, anybody system that you can describe, then you have an experiment in the lab that you can perform with some knob that you can turn. So a simulator is something that allows you to map the same Hamiltonian, so you reproduce the same dynamics and observable of the system that you want to know, and you can, for instance, high energy physics Hamiltonian of some crazy interaction of quark, I don't know. But then you have optical lattices. Maybe your optical lattice experiment is able to map the same Hamiltonian, but that one you can tune, and so then you could do the experiment and measure observable there, and you could get information on the model that you are simulating. That would be an ideal definition of a quantum simulator, an analog one. But we are still very far away from that too, apparently. What people say is that it's very, very complicated. We had a talk by Sirac that 1 year ago that gave an idea of how far we are from that too. More comments?
About the process simply, where does your hardness come from? Is that because of maybe because of the initial states, which is Fox states?
Yes, actually it's a very good question. So U is referring to a theorem that we are going to see in 1 week about boson sampling. So it's the analog of Gottesman and Neal, but for bosonic systems. And what she's saying is that the linear interferometer is described by positive Wigner function. We are going to say this. And so there is this theorem that says that if everything in your circuit is described by positive Wigner functions, maybe you also saw Ingrid's talk, then you can simulate efficiently the output with a classical computer like Gottesman and Neal. In boson sampling, you have a double negative Wigner function. It's both the input, because the single photons have a negative Wigner function, and the photon detector, POVM, have also a negative Wigner function. So it's doubly redundant, it's redundant, and then we will see that it has been possible to reduce this. It was a bit, we said, okay, boson sampling is overkill then. Is there some model that is less Wigner negative and that is still hard to sample? And we could answer positively to this, and we are going to see this in 1 week. Okay, we can conclude it here.